Okay, this is case B with the laminar flow. We're doing the exact same thing with our geometry and meshing. I'm just redoing it for the sake of this video. Just going over the process again. So the next couple of minutes are just outlining, the steps that I took to get the mesh that I want with the resolution necessary to do the simulation. And for this setup, the only thing that I'm changing is this viscosity to 0.015. The density is 1. Our method is laminar. So we're changing our velocity to 3. These are our reference values, and we're still computing from the inlet. And then for initialization, we're doing it the regular way with 25. And then we're going to run our calculation with 500 iterations. And we see that it converges very quickly at 112, which is good, and a telltale sign that our mesh is good and we have the correct settings. So here I'm creating our contours, which looks good because it's still symmetrical. And then for our velocity, we can see that it has a more defined sort of contour than our previous case with inviscid flow. And then here I'm getting our data for the pressure coefficient, which is a good graph. It's a similar graph for the previous case, and I think it'll be that way for all of the cases. And so is our velocity, which is just a constant level. So here we have our drag coefficient, which is a 0.888, which is much higher than our inviscid case, which is a good sign because we have more of that developed flow with the laminar, and there's more friction between the fluid because we have like the layers within the fluid are more developed, which creates that drag. So here we're recreating our contours for the pressure and velocity, and then we're going to end this video by doing the streamline for our simulation.